introduction. So welcome to another installment of our Sustainable Energy Seminar series from the Wisconsin Energy Institute. My name is Scott Williams. This is your first time joining us. Thank you for being here. And if not, if you're a returning member, we thank you for being here as well. So I'm the education manager at the Wisconsin Energy Institute and the host of this series. And we do the Sustainable Energy Seminar every other week in the fall and the spring. And our goal is to highlight the cutting edge energy research from across UW-Madison, as well as showcasing how different disciplines understand energy challenges and develop solutions. So throughout our series, we'll hear from different disciplines and how they understand energy challenges and develop solutions. And we'll hear from folks in science and engineering, as well as social sciences and humanities, to learn about the ways in which they view these challenges and solutions. So this seminar is open to the public, but it's also a course for students in the undergraduate certificate in engineering for energy sustainability, as well as the master's in sustainable systems engineering. And we offer this through Zoom webinar. If you're registered for today's webinar, you'll be registered for the remaining webinars for the rest of this semester. Live captioning is available for those who would like to use that feature. You can click on the Show Captions button at the bottom of your screen in Zoom. And if you have a question, please use the Q&A box. If there's an appropriate time to interrupt for a clarifying question, you can do so. Otherwise, if it's a longer question, we'll have time at the end of the presentation for any Q&A. So with that, I'll introduce today's speaker. Xiaopeng Li is a professor in the Department of Civil and Environmental Engineering and an affiliate in Electrical and Computer Engineering at UW-Madison. He leads the Connected and Autonomous Transportation Systems Laboratory at UW, and he also directs the Rural Autonomous Vehicle Research Program for passenger transport, which is funded by the U.S. Department of Transportation. Prior to joining UW-Madison, he also served as the director for the National Institute for Congestion Reduction. And his major research interests include modeling and field experiments of connected, electric, and automated vehicles, as well as transportation and infrastructure systems analysis. So today he'll be talking about the trade-off between safety, mobility, and energy on automated vehicles. So welcome, Professor Li.
Thank you, Scott. It's a great honor and pleasure to take this opportunity to talk about energy and sustainability from the perspective of transportation, particularly autonomous vehicles or automated vehicles. So I'm gonna put this talk in more of a broader aspect in addition to energy, because we also have safety and mobility and these factors that we want to consider in a holistic transportation system. So please feel free to leave your questions or comments in the chat box. I'll try to monitor the chat box, or you can just interrupt me anytime if you have questions. I'll make the presentation less technical as we go. Sure. So, all right. So let's say I want to talk about very high hopes of autonomous vehicles in the starting from 1990s. Probably most of you have heard of autonomous vehicles, this term. And back then, people wanted to augment autonomous vehicles or automated vehicles with connectivity, that is communications, with via infrastructure or vehicle to vehicle or vehicle to everything communication. So the hopes were like this kind of technologies will improve transportation systems substantially across all aspects. Safety, reducing like over 90% of crashes. Mobility is going to be double or multiply the capacity. Energy's efficiency is going to be improving to more than 50%. So there's lots of studies in the past that had very optimistic predictions of the autonomous vehicles or broadly speaking, connected and automated vehicles, CAV's technologies. And what was more exciting was actually this kind of technologies was piloted in 1997, and where every vehicles follow each other with very short headway at the speed of 60 miles per hour. back then people could have a vision that, okay, our future transportation would be look like this. I mean, all vehicles are smart and closely follow each other and can, the intersections of our transportation systems can be orchestrated autonomously, safely, harmoniously with people and other users. Of course, this is just animation, and I'd be scared if I walk across the intersection like this. But anyway, this is a CGI to show you computer graphics to show you how the system could be like. So there are already lots of deployed technologies like Waymo, Cruise, and some other companies like Ford and Uber have already tried out autonomous vehicles. And you see other modes of autonomous transportation, like shuttle has been demonstrated. The autonomous trucks are there, and on campus, actually, we have autonomous delivery vehicles by Starship, I believe, and also in some restaurants, you see this kind of a delivery robots, right, in closed environment, in hotel or in restaurants. So the production automated vehicles actually have already been penetrated a lot in the market. I'm talking about vehicles that with automated features that you can buy from dealers actually. So there has already been quite a lot of new cars installed with L1 automation. That basically means like adaptive cruise control that can control vehicles longitudinal movement automatically, or 50% with L2 level 2 automation. That means okay, vehicles can control its longitudinal movement and also like following the lane keeping to make curves, to turn along the automated lane. Yeah, along the like road geometry. So when I say like L1 automation, the key technology is called adaptive cruise control, which is a significant part of advanced driving assistance systems, ADAS. All right, it's just going to be following the preceding vehicle automatically. And if you have a car like that, it's just like cruise control, but it allows you to set up the following distance, and it can automatically react to the preceding vehicle to adjust its uh, following spacing. And you're going to see on your dashboard about the like following spacing, and some of the newer versions will show you the detected vehicles. So let's say with this kind of deployment, how much of the earlier like 1990s visions has been accomplished? Tesla's reported like they have significantly reduced the crashes. When their AV technology, they call it full self-driving or autopilot. When they're activated, they can actually reduce a lot of crashes. And there are other reports that are saying, with automated vehicle technologies that can significantly reduce a crash. So we're on a good track of reducing crash. And what about mobility? Mobility, I think these are a little bit in my field, but I want to say, you can just look at the highest point of this graph. This is from the railroad, the human-driven traffic data. And this says how many vehicles per lane regular roadway can accommodate, about 2,000 vehicles per lane per hour. And we also measure that for production automated vehicles with different headway settings. So overall, like the capacity are about the same or similar levels. Or, some of the headway setting will even make it less than a human-driven vehicle. So still mobility, we haven't multiplied the capacity. We're doing something similar to current actually human traffic. So what about energy actually? When we talk about energy for transportation consumption, what makes changes are this stop and go traffic, all right? Whether you stop at the signalized intersection or you're involved in frequent slowdowns in morning congestion on freeways, they're gonna cause lots of extra energy consumption. So, And we tested the automated vehicles. They're also having lots of stop-go traffics in earlier technologies. I mean, recent technologies we haven't included here, but we see some improvement about this aspect. They're going to have more stable traffic, which means um, less fuel consumption, less energy, and less uh, environmental footprint. So we see actually, if you're looking to the industry, seems like of course, number one thing is the safety. There's nothing relevant if you don't talk about safety. So they put a lot of effort to improve safety. Whereas energy and mobility are like side products. If they can improve energy and mobility along the way, that's going to be great. But they have to put most of the resources on safety first, and then gradually solve energy and mobility problems. So seems like there is a trade off between the mobility and energy and safety. So this study, actually, I want to talk about this kind of trade-off. So like from the public sector, like infrastructure operator, like Department of Transportation, of federal, of state, of cities, counties. Okay, they all have their vision is like we're gonna use this technologies to improve all aspects of transportation. I mean, some of the tech vision is like so-called cooperative driving automation. It's gonna be like improving mobility sustainability while ensuring the safety. So it has a very a profound and complex framework, but what it means is actually making the vehicles work with each other, collaborate with infrastructure units. For example, I'll give you one scenario about eco-driving along a signalized intersection. Think about this as a road that goes to a traffic signal light with green, red alternating signal patterns, and this is the time horizon. And each curve is the time space pass of a automated vehicle, AV. So if the system is well coordinated in the CDA vision, actually, you don't have to stop at the red light. You can just, plan your trajectory smoothly to glide through the intersection without stopping. And this way, you're going to maximizing all these performance aspects. You're going to have almost no stops. And that saves energy, avoids rear-end collisions, and also improves the mobility throughput of a signalized intersection by reducing the lost time due to stops. But however, that is really difficult to accomplish or implement in the real world to coordinate all these vehicles and infrastructure units. I mean, there are lots of reasons behind it, institutional policy, but there is also an engineering reason that is actually, if you're looking into production autonomous vehicles, the they cannot get very accurate control following a particular command. I mean, this graph shows, okay, we gave them a command to follow over time to follow the speed, the profile of this orange trajectories, but their actual vehicle speed responses, their different vehicles with different settings have quite dramatic errors from the targeting speed. And therefore, it's difficult to make this kind of exact control happen. So here is to show the trade-off. Okay, this is your target trajectory. If vehicle can control the target trajectory exactly, you can plan them very well. So one vehicle can closely follow each other, forming a short platoon. That's going to have a energy benefit as well as safety and mobility. But in reality, because you cannot follow this trajectory very well over time and space, I mean, you're going to add a lot of safety buffer. Therefore, you cannot follow the preceding vehicle very closely. And that's going to, basically, you're going to add extra spacing to follow in the preceding vehicle. That adds some overhead to mobility. So then I'm going to talk about some of our study to quantify this kind of trade-off between safety uh, and mobility as well as energy. And then we're going to talk about ways about how to improve this. So first, I'm gonna talk about an analytical model. I know maybe not everyone's from engineering here, so I'll be really going through the slides. It has equations, but don't worry if you don't understand it. Then I'm gonna go to the fun thing about field tests, and then I'm gonna talk about how to use better controls and other mechanisms of improving the system to have gradual improvement about energy, safety, and mobility. Let's look into the model. So I'm not gonna talk too much about the equation, but I'll give you the intuition. It is like like if a vehicle, this is AV, follows a preceding vehicle along road lane, and you're gonna leave some buffer spacing for safety, and also, leaving some other spacing for control errors. Like it's like vehicle follow preceding vehicle. If you're decelerated, you may get closer to the preceding vehicle, and if the preceding vehicle accelerate, you may get away from it. So the following vehicle has some kind of variation or in relation to the preceding vehicle's position, like there's some relative speed difference. So the following vehicle may oscillate. So you're going to have some of the time lag to absorb the oscillation, as well as leave some safety buffer in case the oscillation goes too much. And you want to make sure that safety buffer is always going to be sufficient to absorb the overshoot of the oscillation. So, okay, so with that, you can put some parameters that represent safety, mobility, and stability. Stability is actually very much relevant to energy consumption. You can equivalent this as energy consumption or environmental impact. All right, so there's some analytical design about it. I mean, you're just formulate the equations with very simple parameters that, simplest parameters shows the like this delta is a safety buffer, and this kappa here is actually how sensitive we react to the preceding vehicle's deceleration and acceleration. If the preceding vehicle decelerate, you may decelerate, but how sensitive that is captured by K here. And also tau is like you're gonna leave how long this gap is. The longer the gap, actually, is gonna make the capacity drop because it takes a longer time for one vehicle to pass that point on the road. But the benefit intuitively is it has more gap that can absorb this kind of oscillation. So, okay, so we actually, with this formulation, we're gonna come up with some robust design and doing some optimization. It's very complicated equation. I'm not gonna talk too much about it, but with all our effort, maybe you can think about like 10 pages of math or formula derivation. We solved the relationships between these parameters, and I think we can take a little bit about this. You just ignore the math, but I want to say this is like delta decreases with both kappa and tau. And maybe this is something I can explain. Kappa and tau are actually relevant to the stability. Okay, bigger the kappa and the bigger the tau. Actually, you're gonna have I think better stability, but then sorry, actually worse stability. But that means your delta is actually bigger, and which is that safety is going to be better. So basically that means, okay, so this means if you want to make the system more stable, you have to add a safety buffer. And so this vehicle, if you have more safety buffer, the system is more stable. And that's going to make a system safer, but compromise. It's going to be help with energy, but it's going to compromise the mobility. So, and there are something like this. Okay, I'm going to skip it. It just shows that these parameters are going that way, and this parameter shows our trade-off. So, and I'm gonna basically, if you ignore the mass, that means if you want to improve the mobility, you're going to sacrifice the safety or safety risks. You're going to increase the safety risks. Or if you want to improve the safety, you're going to sacrifice the mobility. Um, and and also, with some frequency domain analysis, I mean, look into how traffic following vehicle oscillate with a preceding vehicle. Anyway, I'm gonna skip the mass, but you're gonna find another properties. If you want to improve the mobility, you're gonna increase the traffic oscillation. Vehicles gonna tend to be more stop and go, and it's gonna increase the consumption. So, I mean, the math is complicated, the proof is complicated, but the conclusions are verifying somehow our intuition. It's like I can give you extreme examples. If everybody, really have a very long separate headway from the preceding vehicle. Let's say if you're always keep your vehicle 1 mile away from the preceding vehicle, you're not gonna have crash risk against the vehicles, but the traffic is not gonna move. Think about Madison. We don't have enough roadways to accommodate that kind of traffic, right? So therefore, mobility and safety is a trade-off, and a mobility, and also, um, mobility and energy consumption is also a trade-off. If you want to push vehicles like through the system faster, then the vehicles tend to have more oscillations and stop and go and congestion. Yeah, and that's going to create the extra energy consumption. All right, so we have this, and we did some field verifications. We have the theory and the revisions, but let's do some field experiments. So we used our lab has a couple of these vehicles. They have like production vehicle, automated vehicles. They have ADAS functions, adaptive cruise control. Those are like autopilot. We put some of the equipment like GPS and it record the data, and we test them in a place called Tampa, where I worked before, Tampa, Florida. Tested the vehicles in these sites, and we actually did some experiment with one AV following another AV, or two AVs following a reference vehicles, and then we changed the speed, created some realistic deceleration acceleration patterns, and then these are the speed profiles we collected, and these are for two vehicles, and these are for actually multiple vehicles. So what we do is we actually get the data and feed the data into the model we proposed, and we extract the parameter values, and the fitting is pretty good. Like look into the fittings, they're as high as like 90 or 80%. I mean, R squares goes all above 0.8, very good fitting. And then we can look into some of the new interesting things. The headway setting is like 1 is shortest headway, 4 is the longest headway. And that maps to our tau very well. Like tau increases with the headway settings. And headway settings also actually following gap headways. These are just the same intuitively. The headway settings are have been well explained by our parameters. And then here are the findings. Delta increases, the tau is going to decrease. This K or kappa increases, tau is going to decrease. So these are exactly well matched with our theoretical prediction. That is actually our theory predicts that one variable increases, the other variable is actually going to decrease due to the trade-off. And this study actually will explain that trade-off. And then we also look into the stability, and also I'm gonna skip the mass. So basically what we did is we're gonna look into how this kind of oscillation being amplified from a vehicle to another vehicle. We tried the different speed cycles. This is short speed cycle. It's like every 18 seconds, I'm going to have deceleration, acceleration cycle, versus this 26 seconds, I'm going to have a deceleration and also acceleration, longer cycle. I look into the amplification ratio. That is the following vehicle's oscillation divided by the current vehicle's oscillation. We're going to see as this headway increases, this extreme amplification decrease. That means the headway increases, oscillation is going to decrease. So shorter headway, this vehicle is going to do this kind of high oscillation. Longer headway, this vehicle is going to be stable. All right. That explains the theoretical prediction. Okay, we verify these results with another set of data collected by different university, and the fitted value will match the theoretical predictions. It's like they have this kind of trade-off actually. So yeah, this is interesting because the theoretical results will match the field experiment. And actually, when I proposed this, my students actually thought it might be just a theory, and I don't believe it. Then I asked, go ahead and prove I'm wrong. And then they did the experiments and proved and proved that we were right. Actually, that was good. Okay, or in a parallel universe, if I was proven wrong, I'll be also happy, maybe most likely equally, because we also have some other discoveries. But I mean, this time we're fortunate to have it consistent with our conjecture, and that explains the fundamental trade-off, and that governs the industry's design. Okay, if I have a simple system, if I'd rather like to maintain the safety part rather than going too far on to also make the mobility good. But then eventually from the public sectors, we hope that we always put safety first, but we also want to improve mobility and energy, consume energy efficiency as well. So is there any like a takeaway from these studies that how we're gonna improve our AV vehicle control system designed to improve the energy and mobility altogether with safety? Yeah, sure. First is improve the control, actually. If you have a bad control, you cannot have vehicles stably follow the preceding vehicle. That's a problem, So how we can do that? Do nothing about the production vehicle, then you have to add sufficient safety buffer or compromise mobility energy benefits against the CDA vision, or improve the vehicle control precision. What we do is we're gonna, instead of the classic like feedback like PID control, we're gonna use model predictive control, and we're gonna also use AI to do some reinforcement learning to improve the adaptivity of that vehicle. And we did some of the tests with small vehicles, and we found that okay, after we make the control more on about reinforcement learning, you're gonna have much better control outcome actually. Here is like online learning. You're gonna see the actual control and the reference trajectory is very close compared to the original PID control. There is a big gap. And these are some of the tests that we have to have vehicles following each other and forming the platoon, and they can run very smoothly. If you translate that into full-scale tests, that means vehicles follow each other stably with very short gap. Okay, and we also did some of the field experiments with our full-scale autonomous vehicles, and we have similar findings. And we did some of these facilities are used to showcase, at lots of engineer expo, and we're also, this is before I moved to here, but I joined UW-Madison 3 years ago. We also have a lot of good demonstration of the facilities that we have. And then another way is actually we increase the coordination with the signalizing infrastructure to add more connectivity. And this is an example, a field experiment we did. It's just using one vehicle to smooth the traffic. So think about here is actually a downstream, there is a traffic light. It's red and it's going to turn green. So these are human-driven vehicles. And the one that is highlighted in this red box is actually autonomous vehicles. So what you're going to see is autonomous vehicle will communicate with the traffic control, and then we'll just will not join the fleet of a preceding vehicle to stop and then go. It's going to glide us through the signal intersection with a carefully planned vehicle speed. You're going to see these vehicles will go down and stop at the intersection, and this vehicle will slowly join the queue. All right, and then go there without the full stop. That is very nice. And we also did the test with Argonne National Lab, but actually this, let me see, okay, this was a video, but anyway, we tried out this kind of signal coordination with multiple signal lines intersection, and it works as well. And so integrating with the connectivity is going to be a great element to improve the vehicle's performance. And you know, we actually did the study, used the Shanghai data, and also we found that okay, production AV's energy performance may be even worse than human drivers due to delay and intersections. But if we add CAV, that's gonna improve the energy consumption and yeah, and also improve the overall system sustainability. And we also worked on similar technologies with US DOT and US DOE to hopefully using communication to improve the traffic and make it smoother and faster. Of course, electrification is also another way that we look into. Electric vehicles have different powertrain structures as compared to ICE vehicles. And we actually tested the hybrid and electric vehicles, like the vehicles we tested before hybrid vehicles. And I have wonderful students who actually donated some time of his Tesla vehicle, and we did some data collection, and we compared the you know, ICE vehicle and electric AV and hybrid vehicles performance for looking into their velocities profiles over time, and we showed their like stability and also mobility. We're gonna find that okay, if you're looking to these profiles, I mean, they have similar traffic flow capacity, but but actually, you know, as your density increases, the electric vehicle has higher capacity, and because it has better stability. Um, Yeah, so that means maybe electrification could also make the vehicle's response more fast, and therefore you can control it better. Therefore, you can actually also, besides the intrinsic benefit of you know, of having lower energy consumption batteries, zero emission batteries, you can also improve the overall sustainability by even better traffic impact. You're going to have smoother traffic with probably closer headway, right? Okay, so, but we are also looking to actively look into some newer technology like foundation models, vision language model, model prediction control, and a high level decision making, and you know, for high vision, this kind of foundation model can use high level decision making and using classic control for lower level vehicle control, and then you have you can have that flow chart to uh, really actually integrate to like vehicle language models and ChatGPT type of intelligence to improve the autonomous vehicle driving, you know, realize end-to-end vehicle control and to improve the vehicle performance. And we actually did some comparison, and we found out actually that these are some yeah, compare the baseline controllers with our proposed controllers, and we found out that our proposed using VLM like foundation model controller will make the system safer without losing the mobility or um, energy, and actually improve the energy consumption due to the less oscillation. Yeah. Anyway, these are just to comparing different language models, and they all have good improvement. Yeah, I'll just stop here just in case if you have questions. Right.
Great, thank you so much. Yeah, feel free to ask any questions in the Q&A box. So it sounds like, one benefit for switching to electric vehicles is you can control them a little bit better, so then that improves the mobility aspect. Is that right?
Yes, right.
Yeah.
And also, like less stop and go means better energy profile, and the same battery can run the vehicle longer.
Yeah, and I know there's already a big efficiency gain just switching from internal combustion to electric anyways, so that just adds a little bit icing on the top, I guess you could say.
Yeah.
Um, don't see any questions coming in right now. So what's sort of your next steps, or what are you looking into for the future to improve, controls of these systems?
Yeah, in the future, I think the technologies are already there. On the one hand, I'll keep try out the connected vehicle technologies. On the other hand, is like we need to really understand, because right now autonomous vehicles are not just futuristic; they're already around us. Tesla full self-driving, which is pretty much close to high-level automation, and we also have Waymo and uh, you know, like we and May Mobility, all these companies are deploying their autonomous vehicles in selected cities. And in Wisconsin, Racine's also got some demonstration. And so with all these technologies are around, how do we understand their performance? So we're going to need to collect a lot of data and to build reasonable scientific models and predict their performance in safety, like crash risks, mobility, like if the significant penetration rate is there, how much extra congestion it will add, or how much congestion it will reduce, it will mitigate, and also the sustainability. What's the impact of the energy consumption? What's the impact to the emissions, and we need to consider the electrification as well, because some of these automations are always in conjugation with electrification. That also brings lots of impact to the environment. Yeah, sure. So that's actually basically we're gonna need to collect a lot of data and try to set up a methodological framework to evaluate the overall impact of this incoming, actual ongoing autonomous vehicle technologies in terms of mobility, safety, and energy.
We got a question from Sandy, who's curious about sort of the life cycle assessment of the use phase, versus, yeah, so the use phase of consumption of vehicles versus the total life cycle assessment of either comparing electric vehicles to internal combustion engine vehicles. So I imagine, there's a lot more energy that goes into, making the battery and the life cycle of this, of the battery, but how much of that is gained through some of the more efficiencies in during the use phase. I don't know if you have any idea.
Yeah, sure. So I mean, I haven't done like particular life cycle analysis myself, but I can only cite some other study. There are plenty of studies showing that even consider a whole lifetime cycle. Like in speaking of cost, maybe you can. There are some studies saying EV is more, some studies saying ICE vehicles more. But in terms of energy consumption, still like for urban traffic, actually EV is going to consume less energy overall, considering a life cycle, because operational phase it has lots of savings. And sometimes that the vehicle batteries can be reused, and there is a tiered reuse of the batteries as energy storage or something that will further make the electric vehicle settings more appealing. Yeah, sure. So I guess my personal preference is I know that electric vehicles, better technologies are still improving their relative nascent technology compared to ICE vehicle. ICE vehicles are already being optimized to like 99.9%. I don't think that there's going to be a lots of technology improvement, but maybe for electric vehicle, there is still a bigger room for technology improvement. And I hope, over the time, the performance of electric vehicles can be even better and can justify more savings. Yeah.
Yeah, and I think it really depends on how you drive the vehicles. And so, yeah, for a environment like more urban transport where there's a lot more stop start, electric vehicles have more savings that way. And then it also depends on sort of how often you drive something to make, even if electric vehicles have more energy embedded in, the actual battery and the rest of the vehicle to start with, if you drive that vehicle quite a bit over time, then that can sort of make up for the initial kind of energy penalty. Any other questions before we wrap up here? Seeing anything in the Q&A, so I think we'll leave it at that. Thank you so much for your presentation, and good luck in your work and bring us to a connected, automated future for transportation.
Thank you. Thank you, everyone.
Have a good day.
Bye-bye.